Hey, chemistry team, it's your chemistry coach coming at you for video number 2 of our common ion effect buffer titration chapter, number 17 for us. All right, we have looked at one application of the common ion effect, mixtures of strong acids, weak acids, or strong bases, weak bases. Made that into a very simple problem. Now this one will be easy, no new concepts, like nothing. We're just combining Le Chatelier's principle, i.e. the common ion effect, with the traditional ice tables and weak acid, weak base equilibrium systems we've looked at, just putting the two together. So nothing new, but this is going to be a long one. So I'm doing this as a separate video. Hopefully you can attack this. Here's the type of problem you will very likely see on your next exam, my friends. Pay attention. If your coach says it, you should probably listen. All right. This is a two-parter, right? What is the pH and the percent ionization, which has that symbol alpha, by the way, of 250 milliliters? Note the naked decimal point. Makes that trailing zero significant. That's 3 significant figures. Of a 0.12 molar ammonia solution, recognizing ammonia as a weak base. So really, you don't need the 250.0 milliliters for part A. You don't need the volume, you just need the concentration. Pause the video and do that for me real quick. You should be able to whip that out real fast. Do your Q versus K, do your ice table, set up your equilibrium expression in terms of X, do your assumption to try to minimize the mathematical difficulty. If not, you have to use the quadratic equation. Solve for X, and from the X, figure out your pH and your percent ionization. Do that for me with just a plain ammonia solution. Nothing new. Back to the earlier parts of the prior chapter. Then, let's take that same ammonia solution, that 250 milliliters of a 0.12 molar ammonia solution, and let's dissolve in 2.2 grams of ammonium chloride solid. We're going to be making, and give it a shot. See if you can do it on your own. We're going to make the assumption that adding the solid to the 250 milliliters of ammonia solution does not increase the volume. So the volume is going to stay constant when we add the solid to it. We're making that assumption ahead of time. Go ahead and do the same thing. Set up the Q versus K, the ice table, the equilibrium expression. All that's going to be exactly the same. But the values for the equilibrium concentrations for one of your species is going to be a little different in part B versus part A, which changes your value of X, which therefore will change your percent ionization and your pH. Give it a shot at least for part A. You should be able to nail that one out. And if you feel daring, try part B and see if you get what I get. So I'll erase the board and do part A for you. Okay, I'm going to walk you through this in real time rather than pre-writing it up on the board. We should be able to walk through this pretty straightforward. Hopefully I can get it on one board. If not, I'll have to erase it and continue on. So I set up, first thing, my equilibrium equation. There's my ammonia. It's taking an H plus from water to form the conjugate acid, the ammonium ion, and OH minus, the conjugate base. We are after the concentration of that OH minus because from that, we can get the POH and then the pH. And then we'll take whatever X is divided by the initial concentration to get the percent ionization. So we had a starting amount of 0.12 molar of ammonia. Nothing on these, so we're assuming 0. Now we got to figure out which way this baby's shifting because we need to know if they're negative or positive. So Q, again, will be the ammonium ion initially times the hydroxide ion initially over the ammonia initially, products over reactants. Of course, those are 0. You don't even have to do this calculation. You can just say that Q equals 0, which means that's less than KB. Now, we don't know what KB, we have to look it up on the table, but it doesn't matter. 0 is going to be less than that. So this is going to shift to the right. Right, so I'm going to have a negative for my reactants and positive for my products. So let's go minus X for the reactant, plus X for the products. All have coefficients of 1, right? If that had a coefficient of 2, I would have put 2X there. That's it. At equilibrium now, I will get 0.12 minus X for the ammonia, right? What it started with, minus how much I lost. And then the percent ionization will just be X divided by 0.12 times 100. Okay? All right, I'm going to get 0 plus X, or just X of the ammonium ion. 0 plus X, or just X of the hydroxide ion. So again, step 1, do your Q versus K to find out if it's shifting left or right. Step 2, set up your ice table. Now step 3, let's set up our KB expression, which will be just like Q, just Q's initial, K's equilibrium. So that'll be the concentration of the ammonium ion at equilibrium raised to the power of 1 times the hydroxide ion raised to the power of 1 over the original ammonia. Not the original, but the equilibrium ammonia. Oopsie. Raised to the power of 1. Well, I don't know what they are, so let's call the ammonium ion X. Let's call the hydroxide ion X at equilibrium. And then the ammonia is 0.12 minus X. We're going to make that assumption that X is really, really small. So X times X is X squared over 0.12. Let's test that assumption. You can go through and do X, calculate X divided by 0.12 times 100. If it's less than 5%, we're good. Or you can do that shortcut if you want to. And I'll do this in 2 boards. Let's test the assumption. And so let's take the molarity of the base divided by KB. Remember, that has to be greater than 100. Let's look up KB. Let's find that cal value because we're going to need it to do this test. So let me grab my base. I leave all these in a little, there's a cat bed over there under a window, so I leave all my handouts in the cat bed. So there's been cats sitting on this and biting them. This is ammonia, right? So let's look up on our KB table. Find ammonia, which is the first one. So that is 1.8 times 10 to the minus 5, gang. 1.8 times 10 to the minus 5. So 0's definitely, that's slow, but 0's lower. Let's go through and plug this in. Let's take the molarity, which was 0.12, divided by KB, 1.8 times 10 to the minus 5. I get a pretty big number, 6,666. Oh, good to 2 significant digits. That is greater than 100. So this is a valid assumption. Always include that, proving that that's a valid assumption, whether you do it this way or the other way. That's going to give us less than 5% error. So let me erase this. I'll put up a new board. We're going to solve for X. And X is our hydroxide ion concentration. Get the pOH from that. And then subtract that from 14 to get our pH. I'll be right back. I'm back for you, lickety split. It's like time stop whenever I hit the pause button. I can keep moving, but you don't. Ha! I just saw a show called Freaks. It was kind of cool. One of the guys in there could create time bubbles where the rest of the world would slow down, but time would move normally for anybody in his bubble. It was really cool. I love time stuff. All right, here we go. Let's solve for X. So X squared, let's move this over to KB, will be KB times 0.12. Therefore, X is going to be the square root of those. So let's take our 1.8 times 10 to the minus 5th times 0.12. So 2 significant digits across the board. What did I get for X? 1.469 times 10 to the minus 3rd molar. 1.469 times 10 to the minus 3rd molar, good to 2 significant digits. If you look at X on our equilibrium table is the OH minus ion concentration. Let's do this. So X is the hydroxide ion concentration, right? That's 1.469 times 10 to the minus 3rd molar. So from that, I can get the pOH if I take the negative log of that and subtract it from 14. Let's do it. Where's my red pen? So pOH will be the negative log of the hydroxide. Take the negative log when you pee on it. So that'll be the negative log of 1.469 times 10 to the minus 3 2 significant digits gives us 2 decimal places in our logarithm term. So I get to 2.8329. 2.8329. That's not our pH. This is a base, right? So it should be a pH over 7. A lot of students stop there and make the mistake of doing that. That is my POH. So I need the pH, right? Remember, pH plus POH is 14.00, correct? So my pH will be 14.00 minus the POH. So that'll be 14.00 minus 2.8329. 2 decimal places there, 2 decimal places there. So I'm limited to 2 decimal places. I get 11.1671. So that rounds up to 11.17. Now that makes more sense because that's a base, right? It's a weak base. Strong bases are up towards the 13-ish range. So we have calculated the pH of that solution. It makes sense. Let's do the percent ionization. That is alpha. That's an ugly looking alpha. That will be how much ionized, if you look at your ice table, X, over the original concentration of the ammonia solution, which I think was 0.12. Just how much was ionized over what you started with. So X was 1.469 times 10 to the minus third molar over the initial was 0.12 molar times 100. I'm running out of space here. If you go through and calculate it, 2 sig figs, that 100 is exact. I get 1.224. I'm going to erase this 11.17 here. Hopefully you got that down. I get 1.224%, which does not round up. So we get that weak base, that ammonia is ionizing 1.2% for that concentration, giving us a pH of 11.17 rounded. Now let's do this exact same problem in the presence of 2.2 grams of ammonium chloride and look at how the common ion effect hits it. Let me set up the board for part B. Ready for part B? Let's take the same 250 mils of ammonia solution and add 2.2 grams of ammonium chloride and calculate the new pH and the new percent ionization. But first, we need to figure out what the concentration is of the ammonium ion that we're adding, right? The ammonium ion and the chloride ion. So let's take our 2.2 grams of our solute there. Let me zoom in a little bit. So we got 2.2 grams of solute, 250 with a naked decimal milliliters of solution. So we're doing molarity. It's moles of solute over liters of solution. So I have solute amount in the numerator, solution amount in the denominator. I got to convert my grams of solute to moles of solute and my milliliters of solution to liters of solution. You can do either one first, doesn't matter. So let's take the grams of ammonium chloride and convert it to moles using the molar mass. I got 53.491160, good to 4 decimal places. Depending on the periodic table you use, depending on the professor you have, some of them will truncate the atomic masses, right? I use 15.9994 for oxygen. Some people use 16. I use 1.00794 or the James Bond 1.00794 for hydrogen. Some people don't. Whatever. I go out to as many decimal places as the periodic table allows me. That's just me. And you're adding, so you're limited by decimal places. So that gives us moles of solute, right? The NH4Cl, but I'm interested in the NH4+, so 1 mole of NH4Cl produces 1 mole of NH4+. So when it breaks up, you get 1 mole of chloride ion, 1 mole of NH4Cl. And then I convert the milliliters of solution to liters of solution. 2 significant figures, 3 significant figures, 6 significant figures, exact. I'm limited by the fewest sig figs, which is 2. So I get 0.1645 molar, good to 2 significant digits, of the ammonium ion. That's going to be the common ion. When I set up the ice table, or when you set up your ice table, you'll see that that's the common ion on the product side. We're making the assumption the volume doesn't change. When you're adding that solute, that's solid. Now, if it's a liquid, you add those two volumes together. We'll make the assumption that the two volumes are additive if you add the two liquids. But if we're adding a solid, we're going to make the assumption that the volume's not changing. So let's set up our ice table now. So here's our equilibrium. Same thing as before. So we got the NH3. You've got the water. No different. That's going to take it away to form the NH4. I'm going to switch these around real quick. Now, I'll keep it the same. The NH4 plus the OH minus. Can you see? Can you see? Can you see? Can you see it? Yeah. Common ion effect. I have an equilibrium system from the ammonia weak base. I'm adding the ammonium chloride salt. It produces chloride ion, which is not part of the equilibrium system, but it does add NH4 plus, the ammonium ion, is in the equilibrium system. I am increasing that. So that's going to shift to the left and suppress the ionization of the weak base. So I would expect the solution would be less basic. We're going to have less hydroxide. Since we're going this way, we're going to be reducing the amount of hydroxide ion. So the percent ionization should go down, and the pH should go more acidic, so it should go down as well, right? Because it's less basic or more acidic, you got less OH minus. Let's set up our ice table real quick. And you'll see there's only one subtle difference between this ice table and the last ice table. It's because we're going to have some of this present to start with. We didn't have that before. We don't worry about the water. Let's put in our numbers here. So we're starting with 0.12 molar of the ammonia, just like we did before. Now, in the last example, we had 0 of each of these. That's not true in this case. We have 0.1645 molar of the ammonium ion because we added it, and then 0 hydroxide. That's your difference. That right there is the common ion effect, gang. It's the only difference. It's still going to be 0, right? Q is still 0, which is less than KB, so it's going to shift right because the OH minus is still 0. So I skipped the calculation, but it's going to be 0, so it's going to shift to the right. So we can set up our equilibrium table now. We're going to lose one of the ammonia. We're going to gain 1 of the ammonium ion. We're going to gain X of the OH minus, right? Seeing how much that reduces. X should be smaller for this problem than it was before because we're doing the common ion effect and suppressing the ionization of the base. So at equilibrium, we're going to get 0.12 minus X of the ammonia. We're going to get 0.1645 plus X of the ammonium ion, and 0 plus X, or just X of the hydroxide. So in the last problem, that was 0 for the ammonium ion, and that was just X. Now we just plug it into our equilibrium expression, solve for X, which is going to be a little bit different. Do that for me. Calculate the pH and percent ionization and compare them to part A. Whoa, where's my pause button? I've lost it. I've lost it. All right, let's fill this up. So I just rewrote the equilibrium equation. Keep your ice table with you. Let's plug in the equilibrium values of each species into our equilibrium expression. So Kb will be the ammonium ion at equilibrium times the hydroxide ion at equilibrium divided by the ammonia at equilibrium. We don't know them, so we do it in terms of X. So look at your ice table. The value for the ammonium ion was 0.1645 plus X. Good to two significant figures. That's what we calculated with the 2.2 grams of ammonium chloride that we added. The hydroxide is just X, and then the ammonia was the original 0.12 minus X, how much it ionized. So the only difference, again, before, we just had X for the NH4 plus in part A. Now we have 0.1645, the original amount we added in there, plus X, how much we get from the NH3. So when the NH3 ionizes, it produces more ammonium ion, right? But it's going to shift it back the other way. Let's make the assumption that X is really small. So 0.1645 plus X should just be 0.1645 Right, we're assuming x is really small. So if we take 0.1645 minus x, it should just be 0.1645. We'll have to test that assumption, right? The hydroxide ion is just x, and we're going to assume that 0.12 minus x is just x, right? So this will be 0.12. Making that assumption. Let's test that assumption validity. Now we've got two scenarios, but notice 0.12 is less than 0.1645. So if it's valid, 0.12 minus x being 0.12, it's totally valid for 0.1645 minus x being 0.1645. So you don't have to test both, just the smaller one with the higher amount of error. So let's take the molarity of the base divided by the Kb. That should be bigger than 100. We did that before. That was the 6,666. That's the same thing that we had in part A. So that's greater than 100. So the assumption that x is small is valid. If it wasn't, we'd have to do the quadratic equation or something weird like that. So let's come on down. Let's solve for x. So here, x, let's take the 0.12, move it over to Kb. So this will be Kb times 0.12. Let's bring the 0.1645 down. And that's it. We don't even have an x squared term. So this is almost easier than the other one. We got two significant figures here. Let's plug in our Kb. 1.8 times 10 to the minus fifth. That's the same as we had from part A, right? Times 0.12 over 0.1645. That simplifies it greatly. And when I punch this out, I get 1.313. Vertical dashed line after two significant digits times 10 to the minus fifth molar. So in part A, x was, I think, 10 to the minus third something. What did I get for part A? 1.469 times 10 to the minus third molar. So x is a lot smaller, almost 2 orders of magnitude smaller because of the common ion effect. Adding that ammonium ion shifted it back. So now we know what x is. This is your hydroxide ion concentration, right? So we can calculate the pOH from that. We can calculate the pH and the percent ionization. We're done with this problem. We're right here. We might as well get the pH from this, okay? So pOH, since it's on the board, just like we did last time, will be the negative log of the hydroxide ion concentration. We're in the finally doing that 400-meter dash. We're on that last 100 meters, which hurts so bad or hurts so good, depending on how weird you are. So that'll be the negative log of 1.313 times 10 to the minus fifth. Two significant digits in our concentration gives us two decimal places. I get 4.8817. And again, that's not my pH, that's my pOH, because X is the hydroxide ion in this case. Well, now I can just subtract it. So the pH will be 14.00 minus the pOH. Remember, the pH plus the pOH equals 14.00. That's a useful little trick to do it. So let's take 14.00 minus 4.8817. Good to two decimal places for both. I end up with 9.1183. So that rounds up to 9.12. So I get a pH of 9.12. So for part A, look at the pH we got for part A. I think it was like 11.17 or something like that. So this dropped 2 pH units. Holy moly. Remember, pH is a factor of 10. Every pH of 1 is a factor of 10 in the concentration. So go from an 11 to a 9. 11 to 10 is a tenfold change in concentration. 10 to 9 is 10 times 10, or 100 times less OH minus because of that common ion effect. That's pretty crazy. Let's calculate the percent ionization and compare that to part A. I need to erase this board. Did you get it? Did you get it? All right. So now, just like we did last time, percent ionization is just the amount of the ammonia that was ionized, X, right? which was the OH minus concentration, divided by the initial amount of the ammonia. All right, so let's take X, and this is with the common ion effect, the mixture of the 2.2 grams of ammonium chloride solid with the ammonia solution. X was 1.313 times 10 to the minus fifth molar, good to 2 significant digits, divided by the initial concentration of ammonia, 0.12 molar. Take that times 100, convert that fraction into a percent. I get 0.01094%, again, good to 2 significant figures. So that rounds up to 0.011%. That is pathetically small for the ionization. Now remember, for pure ammonia in part A, it ionized 1.2%. When you sprinkled in the 2.2 grams of ammonium chloride and added the ammonium ion, which was the common ion, shifted it back as a Le Chatelier's principle to the left and suppressed the ionization of that weak base, the percent ionization dropped from 1.2% down to 0.011%, right? So the pH, the concentration of X, the percent ionization are all dropping by 2 orders of magnitude. That common ion effect is pretty significant, and we can use that knowledge to control the pH of solutions, right? If I want to take a weak acid or weak base and shift its pH around or percent ionization, I can add a common ion to that, and that's going to lead us into buffer solutions. Hey! Hope you enjoyed this one. You'll see this stuff on the next test.